Go ahead.
All right. Well, thanks for the introduction, and thanks you all. Good morning, good evening, and good night, or good middle of the afternoon, wherever you're at. So, yeah. So this talk, a little bit of preliminary work from Anthony Clark and myself, and let's get the share screen working right here. There we go. So the inspiration from this work really came from a question that Tony and I have had over the years, which is when you look at animals, especially like horses or almost all animals, they're able to walk in many cases shortly after birth. And in evolution, we typically randomly initialize our neural controllers in bio-inspired morphologies. But if you look at those first couple of generations, or maybe even the first 100 or 200 generations, often it's just random flailing about. And so we've always been curious about this, and we think now with some of the machine learning coming about, we might be able to address this. So in this research, what we did, we primarily broke our gait evolution into two parts. So the first part wasn't actually evolution. We used the ADAM algorithm, which is a supervised machine learning algorithm, to pre-train a neural network prior to evolution. And I'll get to pre-training in just a minute. But once we pre-trained a neural network towards oscillatory movement, we then evolved control and morphology in our quadrupedal animats in a more traditional genetic algorithm using lexicase selection. And so the primary question in this work was, what happens if we sort of steer our initial controllers towards effective gaits, or at least effective oscillatory movements before evolution? So our two primary hypotheses off this question are, one, that pre-training will probably result in individuals with higher performance, both on distance traveled and efficiency, and that the pre-training will accelerate the evolutionary process because we'll have an established relationship between the input oscillating signal given to the neural controller and the oscillating outputs of the motors prior to evolution. Now, there's been some work in this area, primarily Stanton and Shannon back in the mid-2010s, looked at pre-evolving neural networks for oscillation prior to embodiment. And that was fairly promising. More recently, we've seen reinforcement learning approaches addressing things like the reality gap and gait generation. And so really in this work, we're trying to figure out, can we combine these two and leverage their strengths? Now, I do want to take it aside for a minute because this is always a challenge with evolution, and this is the Artificial Life Conference, so I think it's maybe a little bit more forgiving than Gecko in this sense. But we always look at evolution as a continuum. It can be a pure exploration tool, just throw a simulation together and see what happens, or it can be an optimization tool. And so for that optimization tool, you're using it more like an engineer, just as a tool in your pipeline. And so in this work, keep in mind, we're using evolution as an engineering tool primarily. So, okay, now that we've sort of covered the bases, let's talk about pre-training for a minute. So our pre-training process, like I mentioned previously, is a supervised learning approach. And the basic goal of this is train a neural network to output a control signal, which in these figures, you'll see as the orange dots, to match a predefined oscillatory desired movement. And that's the blue in this case. So here we've got a simulated motor output oscillating at about, roughly 1 hertz or maybe slightly under 1 hertz. And you can see that this is the result of primarily all the way through the training process. For the first 5 seconds, it very closely matches it. It starts to lose the oscillation here at the end, which is typically where we see it. It sort of trails off. Down here, you see another movement pattern where the orange almost perfectly overlays the blues. So in the supervised approach here, to generate a score for an individual candidate, we have 30,000 samples, which actually matches the update frequency of our physics simulation during the evolutionary process. And those 30,000 samples simply take the desired output, which is blue, versus the orange, take the difference, and sum that over the 30,000. So you can see the result of the training process, a fairly standard loss plot here. Over the iterations, we see loss start to decrease, and by the end of training in a successful pre-training process, we see that loss almost go to zero, in fact. Now, keep in mind, for clarity's sake, I'm only showing one plot here. So this is one desired motor output. The quadruped animal actually has 3 joints on each leg and then 2 spine joints. So there's actually a neural controller has actually got many of these plots combined together to come up with this score. Once pre-training is done, we proceed with the evolutionary process. We use lexicase selection in this work. Lexicase is a many-objective evolutionary algorithm originally introduced by Spector. Notably, we use a couple of modifications to lexicase that have been shown to be effective in the robotics domain. So we use epsilon lexicase selection with a 95% threshold. So the way lexicase typically proceeds, you have a small subset of individuals from your population, you take your objectives, you randomly shuffle them, and you compare your subset of individuals on the first objective in your shuffle. Now, if one individual is far and away the best individual, you select that individual, move on. If, however, 2 individuals are your best individual, if there's a second or third or fourth individual that's actually within 95% performance of the top individual, you move on to the next objective. Repeat the process again. So this is the idea of the epsilon. This works really effectively in these real value domains like distance traveled in a robot, because sometimes, you know, if you go 4 units or you go 3.95 units, that's really not a big difference. So you use your epsilon, you have a tie, you move on to the next objective. We have 7 total objectives in our evolutionary process here. We do use downsampling, which means at every selection event, we only use 4 of the 7 objectives. This has been shown in other works as well. See primarily reference 5 if you're curious about downsampling. But essentially that means we'll only go through 4 objectives. If you had individuals tied through all 4 objectives, you just do a random selection event. And then our tournament size for our sample is 4. So the objectives we have in this work, we've got performance objectives. So these are distance traveled, which is just forward distance traveled in the X direction or the forward direction of the robot. We've got Euclidean distance traveled, which is less restrictive. It basically says move away from your starting point, whatever direction you want to go. We've got the number of touches by non-feet. So we've got a quadruped animat, and if other components of the body touch the ground, we count that as a touch. So we're trying to minimize that objective. We then have efficiency. So we have distance per unit of power. We have the vertical center of mass displacement, which is an objective borrowed from biological observations. So animals tend to not bounce up and down during locomotion because that's a lot of energy to move your center of mass up and down. They try to keep it as stable as possible. And then we try to minimize the number of leg direction switches. So you can imagine when you walk, if you have a nice smooth gait, you only change the direction of your legs at the end of your gaits, you know, swinging forward and then swinging backwards. And this tries to minimize sort of vibrating gaits where the legs actually just kind of move very low and you get a robot that essentially vibrates across the ground, which can be a very stable gait actually. And then finally, we've got one, which is stability. This is the flipped time. We try to maximize it. So in the initial generations, if you have a robot that flips over, that's a low flipped time. It turns out that that evolves to the 10 seconds of simulation very quickly. So I won't show any plots on that. Some of these objectives, I would say, you know, number of touches by non-feet may not just be pure performance. That might also be stability, but I've sort of just binned them to try to give you an idea of the 7 objectives we look at. Our neural network has 33 inputs. So we provide a periodic oscillating signal, 4 touch sensors, 1 on each foot of the quadruped robot in this case here. And then we provide joint feedback for the, let's see, 28 joints in this case. So again, you have a hip, knee, and ankle on all 4 legs. And then you've got 2 spine joints, which all have 2 degrees of freedom. So they can move, legs can move along the main axis of the body as well as away from the body. your spine can move up and down and side to side. The neural networks are built in PyTorch. They have 4 hidden layers with 16 nodes each, sigmoid activation for the hidden layers, and tanh for the output layer to allow it to go from -1 to 1. So the neural networks here, we evolve the weights and the input oscillating signal frequency. Morphologically, we have a 3-segment torso, so front, middle, and rear torso there, all 2 degree of freedom joints, again, the legs. Some notable things about the legs, we have, you can have rigid, actuated, or a passive spine. And then the lower limb segments can either be hinges or they can be sort of a spring-like actuated slider, which would be basically like a shock absorber. So our first experiments, we conduct 4 treatments. We've got no pre-training, which is just let's do evolution as a baseline. Then we've got 3 pre-training treatments. So the first one, we provide random inputs to our joint inputs in the neural network. The second one, we provide zeros to the joint inputs. And the third one, we provide the outputs of the neural network back as joint inputs, simulating a sort of greenfield scenario where the motor outputs perform exactly as expected, the joints move exactly as expected, and the neural network is performing optimally. So in terms of distance traveled, for these first 4 treatments, we see that the pre-training treatments here, the top 3 here, the yellow, the green, and the blue, do more quickly evolve higher distances traveled across the population. In the initial, say, 800 generations, this is statistically significant. But by generation 1000, the no pre-training actually catches up. And so it seems like the pre-training does in fact evolve faster in terms of high performance, but doesn't actually produce statistically significant differences at the end. In terms of efficiency, a similar situation. We see the pre-training again ahead of the no pre-training, but it does catch up. Now, interestingly, at the very first few generations here, you might note this efficiency spike and then drop by no pre-training. This is because in early generations of evolution, you don't move a whole lot. And so if you don't move a whole lot, but you don't, okay, if you don't move across the world a whole lot and you don't move your joints a whole lot, you're pretty efficient at doing nothing effectively. So these are population-wide differences. But again, if we're looking at an evolutionary process, what we actually see is that the best individuals, if we take just the best individuals, 1 from each of the 20 replicates, we see that the joint feedback pre-training outperforms the other 2 pre-training regimens, which is maybe not surprising because this one is providing feedback. But there is a very large disparity here in no pre-training, which I'll allude to in a minute. And that's primarily due to this. The leg direction switches are quite different between pre-training and evolution. So with pre-training, the number of direction switches, and that's kind of how many times you're swinging your legs from front to back, is significantly different. It turns out when we look at the best individuals for that, we actually see that there's a combination. 10 of the 20 replicates have regular walking or trotting gaits, and 10 of them have vibrating gaits. So I sort of alluded to that earlier. It turns out those vibrating gaits, they're somewhat of an evolutionary trap. The populations can't get out of those vibrating gaits, but they're also low performing. And so that explains some of that disparity in pre-training. To give you an idea of what this looks like, you can see this is an overlay of a vibrating gait. There's just not a lot of range of motion here in the ghosting. All right. So from our first experiments, we see that pre-training does accelerate the initial performance in those early generations, and it does seem to eliminate vibrating locomotion. Now, the thing is, vibrating is somewhat of a stable evolutionary trap because it's a stable gait, it's high performing, but it's not physically realistic if you were to realize it in a robot. All right. So in the second experiments, we've got 4 more treatments. So the first 3 are different gaits. A-knees PT is where the knees move opposite of the hips. So if your hips are moving forward, your knees move backwards, vice versa. Diagonal coordination, front left leg, rear right leg, front right leg, rear left leg, coordinated. The third one is 3 legs are in phase, 1's out of phase. So I've got about probably a minute and a half left.
Yeah, at most, yeah.
Okay. And then the fourth one, we take all 3 of those gaits, seed the population equally. All right. What we see is almost a universal convergence to this gait. I didn't want to show a video because it could stutter over the internet. So sort of downward facing posture, rear leg driven, and the front legs used for stability. Similar story here to pre-training previously. The gaits actually, most of them are not super high performing, except for the 3 legs in phase, 1 out of phase. And this is maybe a allude back to Jeff Kloon's work in 2009 with Hyperneat. This was the gait that was in that paper. It's competitive with the joint feedback initially. But let's look at the best individuals. It turns out here was our original best performer. The 3 legs in phase performs very similarly. All 3 gaits together spread quite around. Not a whole lot there. It actually turns out to not be so good. And then also what we see is no vibrating in pre-training, except for when we combine the 3 gaits together. So that might be because we didn't have any protections in the population to you know, limit crossover to similar gaits. So in those second experiments, pre-training and gait patterns might be effective, but we don't really see significantly better performance to the joint feedback pre-training. Which maybe suggests that just a random pre-training process is effective enough. You don't actually need to match a specific gait pattern. We do see that some objectives might limit evolution. The vertical center of mass might be an issue. So going forward, maybe we look at removing that objective. So again, this was an initial exploration into integrating machine learning and evolutionary robotics. Going forward, we actually want to look at using inverse kinematics to generate gait patterns to feed into pre-training, maybe making that pre-training a little bit less random. And then we could ultimately use a loop back using the evolutionary results to inform further pre-training and kind of go in a circular sequence there. All right, so thanks for your time this morning, and I look forward to any questions.
Thanks, Jared, for the interesting talk. Do we have questions while you guys are thinking about some and posting them? Maybe I can ask a clarification question. So the controller was a closed loop controller with recurrencies, or just feed forward?
Just feed forward in this case. So it was feed forward in the neural network, but we did the outputs of the neural network went into the robot. We took the joint angles out of the robot and fed that back to the input of the neural network. So within the neural network, no recurrence, but we were feeding back the responses of the joints themselves in the robot back into the neural network.
Yeah, so it's like closed loop control. But how is it possible that for the pre-training with a random input, how would you then be able to produce a sine wave? Can you maybe explain this?
Yeah, so there was, I should have added that as one line. All of them had a sine wave provided to them. The random input or the zeros or the joint feedback was only to the 28 joint inputs. So the neural networks had, was it 33 inputs? One of those was always a periodic oscillating signal.
Which would also be given to the at evaluation time, or that was not there?
Yes. So during the evolutionary time, during the physics simulation, that oscillating signal was there, and I might have glanced over it in shortage of time. The frequency of that oscillating signal was also allowed to evolve with the neural network. So if they wanted to, you know, if evolution was pushing towards a faster or a slower oscillating frequency, that was tied with the specific neural network as a parameter to evolve.
Cool. Yeah, thanks a lot.
Yep, you're welcome.
Very good.